let's start. So I want to explain one of the tools that we are using to build the ZKVM. As you know, well, I'm Jordi Baylina. I'm from Polygon Hermez, and what we are building is ZKVM with a slightly different approach that many other teams. We are trying to build what we call it a no-code compatible ZKVM. So that means that we want to build a proof that actually takes as an input and state root. It takes transactions, but these transactions are Ethereum transactions, and as standard as possible, Ethereum transactions with the RLP, with the ECDSA signature, with you can create smart contracts, call smart contracts. There's some gas value, so exactly the same that it does Ethereum, and we are trying to reproduce inside ZKVM. So inside to do this inside a prover. So we want to prove that this new state is the one that you get after executing these transactions according to the what we call it, well, what would be a Ethereum standard. This is has a lot of advantages, but it's also a little bit challenging because the EVM was not designed for zero knowledge. So there are a lot of things explicit to the EVM that are not as easy to implement inside the circuit somehow. But we are doing, and one of the important pieces that we are doing is Peel. Just before starting to Peel, just the strategy that we are following from the proof system is we're working with we're creating a Stark. Actually, we are at this point. I can announce that we are moving to the Polygon Zero prime field, and we are using very much the technology. So this can be a Stark, can be a recursive Stark. So we are using all from the proving system. Everything is in the Stark, but we actually want this to be verified on chain. So, and these Starks in general are quite expensive to verify on chain. So what we are doing is we are trying to create a circuit in Plonk or Gross16 that actually verifies this Stark. So it's a kind of it's a proof of a proof. It's a Gross16 proof that's proving a Stark, or if you want a Plonk proof that's proving a Stark. Okay. Just let me just move forward. So what's Peel? The thing is that okay, when we generate this proof, and when we're working with the Starks, the idea is that we want to generate a set of polynomials that have different constraints, different identities that needs to fulfill these polynomials, and this proof that actually these transactions are built correctly. Okay, but how we do that? So we need to build these these polynomials in these relationships between polynomials, and this is where Peel comes up. Okay, so and the Peel is about building, mainly it's about building state machines. So the idea of building this proof is a little bit different than when we're using our 1CS system. In our 1CS system, we have a circuit where we have signals, and then we have relationships between signals. The idea, the similar to the hardware, when we are working with this Stark system with an IOPP system, is mainly that you have like a constraint. It's like the idea is that having a clock. You have a clock, so you have a state, and you have a relationship between the input and the output, and then you just clock, and you have the same relationship, and you are advancing. You have a state machine, you have a clock. Okay, so that's the little bit idea. But in order to design these systems, in order to design this hardware, we need those toolings. We need to build this hardware somehow. Okay, and Peel is very much like that. It's a tool for building these relationships between between signals with the clocks in order to build these state machines. Okay, so and we're preparing it to generate the proofs. So in order for that, let's start with a simple state machine. Okay, it's a state machine that we will use it later, but this is a very simple state machine. It's a state machine Imagine that I want to create a polynomial. Understand a polynomial for the people that's new in that. Just understand a polynomial as a set of values, as an array of values. Okay, and the idea is that we want to generate constraints about these values. We want to generate, for example, okay. So this is the idea. So a state machine, and each value is like a clock. You know, it's just that you are evolving somehow. So in this state machine, what we want to build is mainly we want to build numbers of 32 bits. So we want to have a polynomial that has 32-bit numbers, and we want to guarantee that all the numbers in that polynomial are 32-bit numbers. Okay. So what's the strategy? Well, we will see that it's quite easy to do this, for example, with 16-bit numbers. So having a polynomial that and guarantee that is 16-bit numbers, we can use a plug-up technique. So we have a relationship in polynomials that's quite easy to guarantee that a polynomial is inside a 16-bit another polynomial. But the 32-bit numbers or 64-bit numbers is too huge. You cannot have a polynomial with that many values, you know, reasonable size. And you want to have just but you want to guarantee that. Okay, so how you do that? Well, the idea is you build another polynomial that actually has 32-bit numbers. How we build that? Well, we build with mainly with two steps. In each step, we put the less significant bits 16 bits, the up significant bits 16 bits. So we have like it's like two instructions: a set and accumulate. Somehow, this is this polynomial here. And the idea is that, well, you see that the 3 and the 7, and we put it so here. Oh, sorry. We have the 3 and the 7, and then in the first phase we put the 3, in the second phase we shift, and when we set the 7, the next we just reset and put the next one, and so on. Okay, so you see here it would be like one register. It's a state machine that have one input, one output, has one instruction. In this case, it's a constant instruction. If it's set or reset, just is the 0, 1, and then we have this free input. It's just another. It's a polynomial. It's a register that can be any 16 bits value. So how would we write that in PIL? Okay, because here in PIL mainly, here we define, you know, it's a constant polynomial. Here, one comment. Here, when you see this U16, bool, U16, this is just for packing. This is not, so all the numbers are field numbers. Okay, but this is just a hint for packing. So when you see this, just somehow forget about this. This is not a constraint, it's anything. It's just for internal packaging. But it's comfortable to put it here when you are defining the value. So we have by 32. This is a polynomial that has all the possible numbers between 0 and 2 to the 16. Okay, and then here we define this state machine. It's byte 4. We call it this byte 4. Okay, and here we have a constant. The constant is just, it's a constant polynomial. It's 1, 0, 1, 0, 1, 0. It's the one that we saw here. Okay, this is 1, 0, 1, 0, 1, 0. This is defined. Okay, here we have a committed polynomial. This is free in. This is the input. Okay, this is the one that are 16 bits. Here in this line here, we see that free in must be in global byte 32. This is the first thing that we see. This is a lookup. So we are actually here is hidden all the polynomial identities that are embedded in lookup. So this, when we are generating the proof, this in will be replaced with all the polynomial constraints in order to guarantee that this free in is this inside this byte 2. Okay, so we define also a committed is another committed polynomial, which actually is the out, is the register that we are evolving, and here we define the state transition, how it is. So the idea, if its set is 1, mainly this is set is 1. This means that the second term is 0, and then we just put free in the out register. Okay. If set is 0, then this is 0, and then what we put here is, okay, this is going to be 1. So here what we put is the alt value shifted 16 bits, and then we add the input, and the input is 16 bits. So the out is going to be always 32 bits. So this is a very simple. You see, this is a very simple state machine in order to build just 32-bit numbers. With this, we have the guarantee that out will always be 32-bit numbers. Which one? whichever we choose, depending on the frame we choose, we will have different values. But we have the guarantee that all those values are going to be 32 bits numbers. Okay, so this is the first example. Okay, let's build like another state machine that's a little bit more complex. We call it this arithmetic. So imagine that we want to build sets of values. Each set contains A, B, C, D, and E, and that fulfills this. So at a certain point, it fulfills this condition that A times B plus C is equal to 2 to the 32 D plus E, where A, B, C, D, and E are 32 bits numbers. So what's the strategy? Well, the strategy is we will have 5 registers, A, B, C, D, and E. We have just a free input, so we can put a free input the same. It's just going to be a 32-bit value, the same that before. And the idea is that we will have like a kind of an instruction. So instructions will be just load them and put the latch. So let me go to the. Well, the idea is this here. You see that we have maybe in the first. So in this clock we load A. So in this clock we load B. In this clock we load C. We load D, we load E, and in the last one we just latch. With latch means okay, this is the valid ones, the ones that we want to commit, the ones that, okay, this is the one that we guarantee that when latch is 1, then A times B plus C is equal to DE, where D is the most significant bit and E is the less significant bit. Okay, so how we do that in PIL? Well, we define these constant polynomials, A, B, C, D, and E. Is A, B, C, D, and E. You see A is 1 in the multiples of 6. B is 1, and so on. So you see here the construction. We have also the constant latch. Okay, we have and then here we start defining free. It's a committed polynomial. We define A, B, C, D, and E. And here is the first interesting thing that we see. We see that free must be included in the byte 4. Byte 4 is actually the last state machine that we defined before. So with this constraint, we guarantee that free is a 32-bit number. Okay, so it must. So the idea is here. I can put everything here. So the idea is I can put everything here. So I can choose any number, but must fulfill this. So I will have also to go to the byte 4 and generate this number in the other state machine. Okay. Here I define the state transition for A, B, C, and D. Mainly is when the set A, when I'm loading A, because then I'm putting A, and if not, I'm just putting the last value. The prime here is the next value. Right? It's in the language. Okay. And here in the last 2 lines, mainly what we are doing is, well, we are calculating mulsum, which is A times B plus C minus C. This must be 0. So this must be 0 when the latch is 1. So this is in the last line. So when latch is 1, in order for this to be 0, this must be 0. When latch is 0, is when it happened. So that's, I don't care which are the values. So while I'm loading A, B, C, and D, because this will happen. Why I put here 2 lines and I don't put in the same line? Well, here what I'm doing is, one interesting thing for the proof is that I'm just working, I only allow doubling the degree in each time. So in this case, A times B is I double the degree, but when I'm doubling the degree, then I create another polynomial, that's a mulsum, and then I do the equations on that. This is very interesting because this is what, we don't grow the degree. So the thing is that when you're doing the operations, you are extending the degree. You do a multiplication, you do degree 2. Then you do another multiplication, you multiply the degree by 4. And then you multiply them and you go to the degree by 8. And this is not good. So what we are doing here is we are in the prover, mainly what we are doing is we are creating what we call it like a quotient polynomial that allows us, with committing an extra polynomial, with the cost of committing an extra polynomial, we can go back to the degree n. So we go to the 2n, but then with this quotient polynomial, we will go back to the degree n. So at the end, what we are trying to do is somehow have as less committed polynomials as we want. But when we extend the degree, instead of extending the degree, what we are doing is just adding more polynomials. Okay, this is more optimal because you don't need to go everything to degree 8 you only go to another, you just create another polynomial, which is much more expensive than extending all the polynomials that you are using in the system. Okay, so this is the trick, and this is why we are putting this explicitly in the language. Okay, so we already have well, here we have two examples of two state machines, one for creating 32-bit numbers, another that's using this state machine for creating multiplications. But actually what we want to build is, we have state machines, we have processors. So what we want to build mainly is a kind of a processor, so it would be a very basic processor. So basic for processor for processing things. So a processor will have generic registers. Here, for example, is A, B, C, D, and E. We have a program counter. So a processor have a program counter. So this is mainly which line are you executing. This is the program counter. We have an instruction. An instruction is represented by a set of polynomials. So if you want, but by a set of flags. Okay, so maybe it's just one bit will be one of these polynomials will be a multiplication, another if it's a move, maybe another if it's a storage write or a memory read, or so each have different instructions. Maybe it's a jump, it's not a jump, and so on. We have also a free input and well, some other registers we will see now. Okay, so how we would do it in PL? Well, we define a lot of all these polynomials. We do this definition of these polynomials. This is just normal definitions of the polynomials. Okay, here is just input verification. Actually, we can do it. All this actually we are doing with a single lookup, but this is just input verification, so that it is a binary number, for example, or that byte 2 or whatever it's maybe it's in byte 2, an address is just in byte 2, so we have different constraints. And let's go to the first interesting thing. Imagine that we want to do a move. How we will do? Well, this is in A, this is part of the instruction. So if you have an instruction where, imagine that we want to move A to C. So in this case, in A is going to be 1, set C is going to be 1. And what we are doing here is, let's see, we are creating this operator. This operator is just, it's a kind of, we're selecting in A, and we are in with in B, to add in B, if in B is 1, we are in C, if in C is 1. So if only in A is 1, or this is 0, so we are just adding A. So in this case, operator is going to be A, and we are just here in A prime, we are just putting, so if set A is 1, then we are putting operator to A, and in the next round. And if not, we are just keeping the old value. And this is very much what's saying here. If set A is 1, then this is op A minus A plus A, so it's op. It's the next value of A prime is op, and if set A is 0, then the A prime is just A. We are just keeping the value. So with this, we can have moves. Okay, maybe there is an instruction, and this is const is part of instruction. There is we can have an instruction for example putting a 4 in D. Okay, so in this case, in A, in B, in C, in D, in E, is going to be 0. Const is going to be 4, so we are adding 4, and set B is going to be 1, and so we are putting 4 in 1. So with this, we can have instructions for moving between registers and for inserting values in registers. We can have also instructions that allows to put any value to a given register. Okay, and this is important because, for example, when we want to do a multiplication, we don't have an instruction. We don't have an instruction in our state machine that's going to do multiplications. What we are doing is we are letting the user to put any value to C, and then checking that maybe A times B is equal C. So this is, we are allowing to put any value and then checking later and forcing to check that this is a multiplication. Okay. Of course, we can have a conditional jumps. In this case, for example, we can have an instruction jump if 0. Okay, so here we have it's a kind of a circuit that we can detect if it's 0 or not. This is what's in these 3 lines here. So this is 0 is going to be is 1 if operation is 0, and 0 if not. Okay, we do this with this in intermediate value in the inverse, which is the inverse of the op, and then filling this we know if it's 0 or not. So if the input is 0 and the jump the instruction is a jump if 0, then we have to jump, and then the program counter will be either, so if the jump is 1, then it's going to be a new address, so we are going to jump to a different address. The program counter is going to go to a different address, but if jump is 0, then we are just going to the current instruction plus 1. Inc is just a normal instruction. It's just it's just 1. It's a constant polynomial. So we are going to the next instruction. Okay. So we have move. We have conditional jumps and conditional jumps, and here is the what we were calling before. We have this multiplication. Okay. So or if you want this arithmetic, imagine that we want to do a multiplication. Okay. How we would do it? Well, we would put it, maybe we want to multiply 5 times 7. Okay, maybe we want to put 5 in A, 7 in B, 35 in C, and then we want, or 35 in this case is in D, and then we want to check that this is valid. How we do? We do this main.arith. This is part of the instruction, and here we have a lookup. So this multiplication that I'm assuming is correct in the main state machine, I'm forcing that this needs to be calculated in the arithmetic state machine that we saw before. Okay, and these are selectors that allows just to do this lookup in in some specific so in some specific rows. In this case, in the case of the main, is only when there is an arithmetic multiplication, for example, it's an arithmetic operation. Okay, and in the other side, in the where we are taking as real values when we saw in the last state machine when latch is 1. So this arith.latch, this is we saw it here before. This is arith.latch. This is when latch is 1. That actually is when these values, we guarantee in this state machine that these values says okay, that this is the real multiplication, and so on. Okay? And this is very important, because you see that we can, with this system, we can have different state machines. We can have different state machines, and with this lookup instruction, this we call it in, this allows us to connect to connect state machines one each other. And this is very interesting, because this is what allows us to do engineering. We can have a state machine for doing binary operations. We can have a state machine for memory. We can have a state machine for storage. We can have different state machines, and we connect them all together with we connect them all together with this lookup. Okay, and we do it in this one line of code somehow. Okay. This is how it would be, for example, okay, we have a processor. If you have a processor, then we have a kind of an assembly. Okay, so would be an example of how this assembly would look like. Okay, here, when you see the $res, $a, this is the free inputs. When you want to, the problem is that when you are executing an assembly, that means that you are building these trays, you are building these polynomials, you need to know, well, it's a free input. It's an instruction that allows me to put anything, but what actually I have to put, okay? And this is what I indicate here. So this is a free input. When there is a $, here, that means that what I'm putting here is a free input, and this is just kind of a language, just a sub-language that tells to the executor, the one that the executor is the program that's building these polynomials. It tells the executor what exactly to put. Okay, so in this case, for example, we are putting result to E, then here we are putting a value A, we are putting a value B, and here, well, here I'm subtracting jump if 0, then it's okay. Here, what I'm doing here is I'm just testing that I have like two values. I have two values that I'm testing here in this program. I'm testing that I have two values, and when I multiply them together, it gives the result. Okay, of course, without checking, and well, it's just it's 232 bits numbers. So I'm just putting the result to E, and you see here in general the first instruction is for the public, is reserved for the public input. Okay, so we have the result to E. Then I put it in a value A. Okay, I subtracting 1, so I'm checking that A is not 1, And if A is, so A plus minus 1 is 0, that means that A is 1. And then I'm saying, no, that's not okay. Okay, so then I'm just jumping here. Then I'm putting B. I'm checking that B is not 1. If it's not, I'm just jumping. That's not okay. Then I'm putting C to 0, D to C and D to 0. And then here, I'm just, this is it's a mistake here. Well, I'm just putting E. Well, I'm just selecting, I'm selecting E. No, it's not a mistake. So I'm just selecting E, and here I'm pushing arithmetic. So in this case, I'm forcing that A times, what I'm forcing here is that A times B plus C, that's 0, is equal to D, which is a number, and times C. Okay, so I'm checking, and if this is 0, if it's okay, then that's fine. So it's okay. But if this is not okay, I will not be able to generate the proof. So this is going to be invalid. Okay. And if it's okay, then I'm just setting everything back to 0, because this is a cyclic program, so I need like to start over again. But this is an example of this state machine, which is a very simple one. Okay. One thing that's important here is, okay, but what instruction? So how do I know that I'm executing the right instruction? So which program is executing? Because here I could put as instruction, I could put everything. You know, these polynomials. So how I fix all these polynomials that set up the instruction in A, in B, and C? I can put anything there. So I need to force that this processor is executing a specific program. It's executing each instruction. It's a specific program. So how do I do that? Well, what I'm doing is, I'm generating the program. Here is this program that we saw here before. Here is the program in assembly. And here is the translation to this thing. In this case, for example, I allow, this is an int free is 1, so I don't put anything number, and then set E is 1. Okay, so this is the program. Here is any number goes to A. In this case is, I'm just putting in A, so I'm selecting A. Here in the constant, I put -1, so I in the op is going to be A plus 1. And then here is jump if 0. So if the result is op if 0, then I'm going to address 8. So this is all together. This is like another instruction. So this is like a set of polynomials all together. Okay, and here is the translation between the program and all the polynomials that represent this program. So okay, I can convert these. Polynomials to a single polynomial. This can be done with, actually we are doing now with just with a random number, but in this case it's just, this is a field, this is a big field, so we are just putting the constant, the address, the line in different places, okay? So the instructions in all them together. So we have a single polynomial where the valuations are these numbers, and then actually what we are doing is, okay, we are just checking. And this is very important. Here in the important is that in the program we are also putting the line. So this is 0, 1, 2, 3, 4, 5. We are setting the line number here. Okay, and the idea is that the instruction that I'm executing here, so is the actual polynomial. Okay, when I build this plus the program counter, which is the line here, is the less significant part in this case. The line here must be in the ROM. Okay, where the ROM is this value. Actually, all this I can do it with just with more, instead of having a single ROM polynomial, I can have like many ROM polynomials and with a single lookup. Okay, but this is the idea, and with this we force that we are executing a specific program. Okay, so we know how to build state machines, simple state machines. We know how to build more complex state machines, and with this we can do state machine that's suitable, that's tailor-made for processing Ethereum transactions. This is a little bit, the idea is the same. The idea is the same that I'm illustrating, but it's a little bit more complex. Here, for example, the registers are not 32-bit numbers, are 256-bit numbers. So we need more registers. In this case, well, these transparencies are a little bit old. In this case, for example, for a 256-bit numbers, we are using 4 chunks of 64 bits. Actually, we are moving to the 64 prim num. So here, instead of having 4 registers, we're having 8 registers. We are at this point, we are adapting all these stuff with this new prime number, but the idea is the same. We have a state root, and we have a lot of things that are quite specific to the EVM. Here we have, for example, we have a gas counter. We have a maxmem, for example, for tracking the memory. We have a context, so that this allows, for example, to do calls. You know, in each call is a kind of a context. And when we are processing a call opcode, then we're doing is we are changing the context somehow, and we can go back. And if there is a throw, we can recover the last state. And so we have everything that we need in order to process the EVM. But the idea is exactly the same. It's a little bit more complex, more registers, but the idea is very much the same. Okay, so before jumping further, so I want to go back here. So okay, here we have the polynomial identity language, and what you need in order. So what's the requirement to build all these? Of course, you need to build the pill for building the different state machines. Each pill, of course, will have some constant polynomials. We have also to build those constant polynomials. And the other thing that we need to build is the executor. Okay, the executor mainly is this polynomial builder. So we have an input if each state machine. So actually, the state machine of the input will have the transactions. So the auto state and the transactions we want to process. So we need to build all these polynomials that we need to build all these polynomials that will fulfill these identities. Okay, but that's it. Once we have these polynomials built, then we can automatically, and this is a process, and this is what we have at this point, and we are rebuilding for the new prime. But what we have at this point is, once we have this executor, so we have these polynomials already generated, then we can actually build automatically. We have all the tooling for building the Stark automatically. We have also, with this pill, we also generate a Circum language that actually is the verifier of this Stark. Okay, so we generate a Circum language. It's a verifier of this Stark, so we can plug this to this Stark, and automatically we generate the proof, and then we can validate. So in order to build so once we have this tool set, we have this system. The only thing that's required, of course, is designing the state machines, creating the constants, creating the executor, and that's it. Once you have the polynomials, then you already plug it to the system in order to build the proof. And this can be adapted to any proof that we want. So any proof that's validating polynomial constraints, polynomial identities. Okay, and this is from the pill. Then you just plug. And this, in this case, we are plugging to a star generator, and in this case, as a Gro16 or Plonk generator. Okay, so if you see the tooling that we have, of course, we have pill, which is just the compiler, but at the end, it's just a parser of this language. Okay, just to put it in a nice format. With this, we are building actually the state machines. We have different state machines of different kinds that we are working: memory, storage, the different binary operations, and so on. We have this assembly, which is an assembly compiler. With this, we create the assembly compiler. We have a ROM, which is actually this ROM. This actually is the program that's running on top of this processor. This program is actually an Ethereum interpreter. It's a program that's reading transactions, hashing them, checking the signatures, removing the gas, or so removing the gas, doing the transfers of the value, calling, maybe creating a smart contracts or executing this as contracts. It's actually it's an Ethereum implementation, written in this assembly altogether. That actually interprets these transactions. Okay, so we have the ROM, we have the executor. Okay, the executor of this that actually is okay. We have this ROM, and the executor is taking actual transactions and is generating these polynomials. And with this, we generate the start, is the start generator, and we also have this pill to circum. Actually, is this tool that's generating from the pill, it's generating a circum. It's generating a circum circuit, and then you can plug the result of the start, to this circum, and this can, of course, we have the verifier, the solidity smart contract that actually validates the gross 16 or the Plonk. Okay, so this is a little bit the tool set that we are building somehow. Okay, I want to show, we have some time. Well, of course, just to finish this in the part of just to finish the project. Of course, this is the part of the prover. All these go together with the node. Here we have a coordinator selector. Here we have the proof efficiency that we released it. Well, we did a post in the Research a couple of weeks ago for selecting. It's a decentralized way of selecting the coordinator, fully decentralized and very simple and very optimal. So on. We also were talking about the bridge. If anybody interested, there is a Make It All in Lisbon. That's I'm talking how we are bridging between L1, L2, or even between L2, L2 bridge. That's quite very simple, straightforward. Actually, this I'm following an idea that comes from the original sharding on Ethereum, just between the communication between shards, but just before Ethereum 2, it's very much in the beginning. So we are recovering some of the ideas there, and we are just this inter-process communication in the layer. That's interesting. If anybody's interested, can go and check it there. And all this just generates a ZKVM. What's the current status? Well, at this point, we are finishing to build. We are now, maybe we'll have a small delay now because we are switching to this. New prime field. This will, with this, we believe that we can increase a lot the efficiency of the prover. We can go with maybe we can get 1 or 2 orders of magnitude faster provers, just switching to this Polygon 0 prime field and all this technology. With that, we also will get the recursion and everything that Plonky 2 already have in there, so we can take profit of all that. And at this point, we are building a testnet already. So we have most of the state machines done. We are building all the foolproof, the start, the gross 16, the circuit. Just have all the stack done. We are doing these adaptations on the prime field, and we hope that maybe in Q2, Q3 of this year, we can have a testnet. It's not a commitment, of course. We are working on that, and we may find something. But the idea is I want to go vacations just with the testnet launch, and then of course there is a lot of audit and going mainnet. Let's see, Q3, Q4 maybe next year. Okay, this is a little bit the plan. And because we have time, I want to, just before finishing, let me go, because I have some other slides that I think are interesting, just for the pill. I think some of the extensions that we are building right now that I think are interesting. One of those is, for example, how we do in order to build a Plonk. For example, a regular Plonk. Let's see if this regular Plonk just would be. This is a standard Plonk. Okay, so how would we write a standard Plonk in pill? Okay, in this case we would have 2 committed polynomials, A, B, and C. We have 3, these constant constraints, of course, you need to build, but these are the permutation, the copy constraints, the permutation polynomials. Okay, this is what tells you which signal is connected with which. Okay, we have the door constraints, QL, QR. The people that's familiar with Plonk should know that. L1 is the first Lagrange polynomial. That means is 1 at the first and 0 at the remains. Here in the pill, we define a public input. Okay, this in one single public input, and it's a of 0, so it's the first element of 0. And here is a new instruction that we are adding to the pill. That's mainly how we connect ABC with according to SA, SB, and C. So SA, SB, and C are the connection polynomials, and we represent with this. Here is the gate. This is the gate constraint. QL times A, QR to B, QO times C plus multiplication A times B. Here you see that I want to go only one. I don't want to extend. So I don't go to extend the degree of the polynomial. So I define this AB, that's which is A times B, and so this is always n to n polynomial. And in the last one, I just put the public input, the initial constraint. That's mainly I'm saying that in the first element of A must be public input. So A minus public input times L1, which is 1 to 0, must be 0. Okay, with this, and this is, so with this, if I want to build Plonk, then of course I need to build SA, SB, and C, which is the circuit itself. Okay, so I need to build this. But here I can use this system to build a start or to build anything of the polynomial. If I want to build, custom constraints or anything, I can add here. I can create the constraints that I want here, so I can generate everything. And I have also lookups. So here I have all the tooling that I need to build like almost everything. I can connect this something. For example, we are using this Plonk, for example, for KECAC. KECAC is a circuit with a lot of binary inputs and so on. So we can have a Plonk circuit in one side, and it's connected to another circuit that actually is more like a processor that's just calculating KECACs in one side. And I can connect both worlds very much automatically. And the other, just other things that I want to mention is, let me just move it here. Permutation checks, instead of is, we can, instead of in, I can have is. Just if I want to not to do a full lookup, I just want to do a permutation check, which is something that's thing. And this permutation checks is very interesting because I can do it maybe with, this is something that we are adding, is with polynomials of different degree. I can have, for example, a state machine with 1 degree, maybe a 2 to the 28, another state machine with 2 to the 23, and then just do a permutation check, but cross-domain permutation check. So just I can, and this is very important because this allows us, for example, to do some state machines that are quite intensive and work with bigger polynomials, and some other state machines that are smaller, maybe with more polynomials that they don't need that quantity. And this allows us to plug them together, and just some specific computations, some intensive computations in some polynomials. And this is also another huge optimization that we can add with the system. Okay, so this is very much what I wanted to show. Let me see if there are questions. I'm sure that I'm just. Let me see. I don't know if you have questions. I don't know if I'm in time, not in time.
Jordi, you go to the sessions chat Q&A. There's
and the chat session. I see the session
Q&A. It's sort of just a tier below it.
2 out of 5, 47, leave. No, this is not.
Oh, no. If you go on where the chat is, so maybe you might need to expand your chat. There should be a little arrow up in the top right corner.
No, this is not. Yeah, Q&A. Yeah, okay, I see it here.
You found it. I think if you go back, I think the questions for this session started with anonymous 33-minute. But this is on slide 8. So
an hour ago. This is what I see here is just 1 hour ago.
No, so that was from the.
Yeah.
So it would be anonymous. So the question would be, in the example on slide 8, is writing free ID in global byte 2 needed? This is very specific.
Where is no, this is Dairas? No, where is people chat?
The Q&A.
I'm in the Q. I'm in the chat, and then I am in the Q&A. Yeah.
Great.
Latest.
Do you see
latest? Latest. Okay, sorry.
Yes, there we go.
Okay,
and if you scroll down a little bit to 30 minutes ago, the first question applied to you, but that seemed very specific to the slide. So
no, but this is the last one that I see is just 1 hour ago.
Last one you an hour ago.
Can you explain a bit more about Merkle tree optimization?
Oh, no.
I think this is the last session one.
That's way old. That's the very one for the last session.
Oh, okay. They are inverted. Okay.
Yes, exactly.
The first one is the beginning. Okay.
Okay, go for it.
34 minutes ago. Okay.
Yeah, that's the one.
It's in the example on the slide 8 is writing free ID in global by 2 needed as free ID is yes, it's needed because when you see U16, this U16, U32, this is not a constraint at all. This is just for packaging. This is we could remove that, and probably it's better to remove, and maybe for this presentation to be better to remove. But for us, it's very comfortable to say that this is going to be a 32-bit element, because then I can pack them in a smaller file somehow. So I'm just, and also give you some checks, but it's not a constraint. It's not a polynomial constraint. A polynomial constraint must be defined as is. It's not saying U32 or saying U30. It's just a formatting. It's just a hint. It's like this polynomial is going to be this way. So forget about this U16, U32 as a this is not a constraint at all. We are here, let me mention this, is we are, as you see, we are evolving this language, and we are working hard, and we are changing a lot of things there. So that's a little bit the reason why we are not publishing yet, because it's like we are adapting, we are changing. At this point, this is very much it's a tooling that's we are doing to build ourselves, to build all this ZKVM. It's a tool for very much for ourselves, but I hope that at some point it's going to be more stable, and we can release it, and you can use it as you want. Does Starkey already support recursion? This is maybe, this is 1 hour ago, sorry. They need to, sorry, I say I need to go upwards. I'm going downwards. That's the way I'm used to. How does performance depend on the maximum polynomial degree? Yeah, well, it's quite linear. At the end, in the Starks, mainly what you need to do, you need to expand those polynomials. That means doing reverse FFT and then an FFT that's maybe two times, 4 times, or so on. So if you have bigger polynomials, this FFT is going to be bigger, and then you need to Merkelize of those polynomials. And Merkelizing, if you have bigger polynomials, the Merkelization process is going to be big. So that's why you want to work always with small polynomials, and the scaling is quite linear. The bigger, double degree, double time. That's generally is quite very much that. FFTs is n log n, but yeah, that's very much rough idea. The example 3D, well, this is what I'm ready. That's a start. No, I'm sorry.
I think there was a question here. Why did you choose to implement an EVM interpreter rather than a compiler from EVM code to a circuit? From Dara 31 minutes ago. Yeah,
well, the EVM is is quite complex, and with this we interpret. So each opcode. Imagine, for example, a call. We cannot put a call in a single instruction. What we are doing is we are doing like a program that's actually interpreting the call, and this gives us a lot of flexibility, because you'd want to do an exponentiation. Well, you can do a loop. Even, for example, at this point, we are considering to do the CDSA as a normal, as a program somehow. So we can mix script somehow. So as a set of opcodes in order to run a specific program. And it's not only an opcode. It's interpreting everything. Sometimes you need to add a value to the state. Maybe sometimes you need to roll back and throw. Here, for example, there is there is a lot of the EVM is fully of tricks and details. The stack, for example, it's like the limit in the stack. The memories, you need to take into account the quantity of memory you are using in order to compute the gas. You want to do. There are different operations, and we cannot stick to one opcode, one Ethereum opcode to one EVM opcode. So an EVM is just a machine that's tailor-made. So if we need to define a specific opcodes for doing specific things, we do it. Actually, we are putting some registers, some specific registers, some specific operations that are very good for that. For example, well, there are details, no? But there is one detail, for example, is about, it's possible. So it's possible, imagine a transaction that's ends up in a loop or is using a resource that you don't have enough resources inside your prover so that you cannot build a valid proof, but you want to execute those transactions. So we need to have a kind of counters of usages, accounting of the usages that you are doing in the resources, so that at least maybe there are some transactions that you just process, but maybe an op process, but you move forward. You prove that this transaction is not valid, okay? But you want to build the proof. It's not enough saying that you cannot build the proof, because then you stop the rollup. So that's one of some of the tricks that you need to think when you are building the EVM. How does performance? Oh no, yeah, this is that spill basically converts the EVM from a stack-based EVM into a register-based VM. If not, how does each instruction connect? Let me see this more to a stack push pop. No, a push or a pop is just an instruction, and actually, what we are doing is we are interpreting this push. So the push, how we put the push is in memory, okay? And the idea is when you do a push is, when you want to process or you get an opcode, we need to first decode this opcode. We have a special instruction for decoding opcodes. You cannot do if this is opcode, go jump here. If you you have a mapping, a jump table for the opcode. So we have a jump table to the push, and then in the push, actually, if it's a push of a specific value, then we parse this, we put this value in a register, and then we copy this register to some place in the memory, and maybe we increment the stack pointer, and maybe we check that this stack pointer is not more than 1024, and if it's more than 1024, we jump to some throw somewhere in the space. But we are interpreting. So we do some calculus that more or less, more in average, and this is depending on the instruction, but the idea is that one instruction should be an average of between 8 and 16, around, let's put it around 10 VM opcodes in average. And this is, of course, this can depending on the instruction. Maybe a call is much more, okay, but a push maybe it's like 4 or 5 instructions. Okay? In the middle, a NAT. Well, again, we are popping from the stack, so mainly it's reading from memory, popping from the stack, decrementing the stack pointer, putting the memory, doing the operation, and then adding to the stack. So these are maybe 5, 6 operations and so on. As I told you, we are not doing, for example, multiplications in the main state machine. We are just assuming that this is valid, and then this is with block up. We have just a state machine where we are doing all the arithmetic. There's maybe multiplications in there, and then with block up, we plug them together. Okay, can-pill proof can be generated in the browser. Not at this point, but it should not be difficult to do. Actually, the way we are building is we are building a lot of kind of test code in JavaScript and so on, and then all the final code is in C++. And maybe at some point in Rust, but it's like the production code, but for testing and so on, it's in JavaScript. So maybe this test code could be at some point be ported to browser, but it's not we are not thinking about that at this point. Is there some documentation about PIL? Yes. If you go to Polygon Hermez, there is a link where there is a full documentation that's already public, and you can check on that. If somebody on the team is listening, maybe they can share the link somewhere in Twitter or somewhere. No, I mean a NAT code needs to pop 2 values from the stack and push the sum result back to the stack. The 2 pops and 1 push aren't reflected in the PIL, just shown as free in. Yes, so actually, yes, you're right. But when is what I explained. When you have a NAT, so the NAT will jump to a specific assembly code. It's a procedure in the assembly code, and what will do this assembly code? Actually, we'll fetch the first number from the stack, but the stack is in memory. The stack is some place in the memory. We have the stacks here, so it's going to be some memory read there. Then we will do the memory read of the second one, and of course decrementing the stack pointer. Okay, so once we have these 2 numbers in the register, we will do actually the operation, maybe with the arithmetic. We will put the result. We will put the result in the free in. Okay, in the result, we will put the arithmetic instruction, so that we guarantee that this free in that we just put there is exactly. So it's exactly the addition of the other 2 numbers, so that this is number, and then this number that we just free in there, we will write back to the stack, or whatever, break back to memory and increment the stack pointer. The stack pointer we're implementing is a more traditional stacks in memory, and we have to do this in memory among other things, because for example, in Ethereum, when you have many calls, each call has like their own state, their own stack. So you need to keep trace of that. So when the smart contract calls another contract, this smart contract has a newer stack. So so you have this case is the context. We have different contexts, and that means there are different pages in memory, and then you access one place or the other. Okay.
Did you get the question about the Booleans?
Yeah, this is the Booleans and the U16s and U32s. This is not any constraint at all. This is just a hint for how to pack in order to teach the executor and anybody that's using PIL how to pack. It's saying you can, if it's a Boolean, you can pack this as a single bit. You have the warranty that's going to be single bit, but it's not a cryptographic constraint. It's not a constraint at all. It's just a way of working. It's just a hint indicating that this should be but it's not a constraint at all.
Cool.
One of the interesting things of the PIL is that we hope that this will help a lot in the auditing processes. So in the auditing process, you should mainly audit the PIL. If you audit the PIL, that means that, of course, you need to trust, of course, the compiler and the tooling that's in there. But specific program, just auditing the PIL should be quite enough, because the PIL is the specification of the constraints that you want to fulfill. Okay, so this is the most important. Probably you need to audit a lot of things more, but this is the most important, and we hope that this PIL language will help a lot in the auditing process.